good to see you again. Myself, Arun Kumar K, Assistant Professor, Aeronautical Department from MLR Institute of Technology, Hyderabad. See, I welcome you all to the course Thermodynamics. In today's lecture, we are going to discuss about reversed Carnot cycle, or we can say ideal heat pump or ideal refrigerator. So, in the previous lecture, we discussed about in detail Carnot cycle, right? So, that is applicable to the heat engine. So, that is what the with respect to the Kelvin statement we already discussed. Now, with respect to the Clausius statement, actually, we are having this reversed Carnot cycle. So, the Carnot cycle actually which we assumed, we need to reverse the directions and we need to assume the process with respect to the reverse way. Then we can able to frame the reversed Carnot cycle, right? So, we will discuss about reversed Carnot cycle in today's lecture. See, what is that reversed Carnot cycle and what are the process we are having, right? So, with that, what are the applications we are having? That is what we are going to discuss in today's lecture. So, the Carnot cycle comprises of reversible processes. So, it is similar to the, so that is why see the reversed Carnot cycle also we are having with respect to the Carnot cycle. So, Carnot cycle actually we are having the reversible processes we are having. So, that is for the ideal processes. So, all the processes can be reversed. So, if it is reversed, that comes under ideal conditions, right? So, in actual cases, we can't able to apply that. So, this is like a Carnot refrigeration cycle. So, we can say in simple word, Carnot refrigeration cycle, right? That is what the reversed Carnot cycle. So, in the earlier lecture, actually, previous lecture, we discussed about Carnot heat engine cycle. Similarly, this is nothing but Carnot refrigeration cycle. The cycle remains same. What is that cycle? What are the process we have assumed is remains same with respect to the reversed Carnot cycle also, right? But the direction of heat and work interactions are reversed. Actually, I said during the expansion, we are extracting the work in the Carnot cycle, in the heat engine, right? Here, the work interactions also reversed as well as the direction of the heat also reversed, right? So, the QL and QH actually we have assumed with respect to that, with respect to in this way, right? Which means towards with respect to the working substance. Here, QL is towards the working substance and QH is towards the atmosphere. Here, the QL is nothing but actually towards the atmosphere. Here, the QL is nothing but with respect towards the working substance. So, that is what the reversed conditions actually we are having. So, the simple condition is nothing but it is similar to the Carnot cycle. So, the cycle remains same, right? Yes. See, here we are having the QL is nothing but heat absorbed from the low temperature reservoir. That is what always same. Wherever we are having the heat absorption with respect to the sink or low temperature reservoir, there actually I supposed to consider that is nothing but QL. The heat transfer takes place with respect to the high temperature or source is nothing but we call it as QH. So, these considerations and all remain same, right? Universally, these are all remain same. And W net in is nothing but network input required actually. So, there actually we extracted the work output, but over here actually we are giving input to the system. That is why the required work input to the system, right? Yes. See, so again, no need to discuss about in detail with respect to the Carnot cycles again, right? See, whatever I said, the arrow mark over here. In the Carnot cycle, actually, you have seen with respect to this direction. This is what QH with respect to that particular heat addition process, right? Got it? So, with respect to this refrigeration system, what happened? With respect to this refrigeration system, to that refrigerant, actually, we are transferring heat from this low temperature, from the sink temperature, from the sink reservoir. So, I suppose to reverse the direction in this way, right? Got it? See, how to reverse it actually? Whatever the process we have discussed over there, we need to come with respect to this. See, instead of 1, 2, 3, 4 and again 4, 1, right? So, in this way we have considered, right? So, this is actually with respect to the clockwise directions we have considered. But whereas the reverse Carnot cycle, we need to start with respect to 1 to 2, right? And after that we are having 2 to 3 and 3 to 4 and 4 to 1. right? So in this way I supposed to consider. See, this is what the isentropic expansion process we are having. Instead of compression, we supposed to consider as expansion. S1 equal to S2 over here. That is isentropic or reversible adiabatic we supposed to consider. So during that, what will happen actually? The volume get increases and pressure get drops, right? And the temperature entropy remains same. The temperature get drops. That is what from TH to TL it get drops actually, right? And then after that actually we are having 2 to 3. So 2 to 3 process is nothing but actually again we supposed to reverse it, right? And we have maintained that as TL equal to constant. So what is that actually again? TL2 equal to TL3, right? So here with respect to this we are transferring heat energy to here, and I have assumed that as isothermal, right? We are having reversible isothermal expansion process, right? Where there actually we have considered over here 1 to 2 reversible isothermal expansion process we have considered. But over here the QL from the sink actually we are transferring the heat energy. That is what the refrigeration we are having, right? So for that you just compare with the refrigeration whatever we are having, or during I said a summer season the air conditioner how it is working, right? It ejecting the heat from the lower to the higher state, right? Where the higher is nothing but atmosphere over here. So here it is the atmosphere higher state, right? There we are transferring the heat energy. That is what the QH we are having. And 3 to 4 again. So the 3 to 4 actually we are having, right? So this is what actually we call it as the here 3 to 4 is nothing but we are having as the compression process, right? So here actually isentropic reversible adiabatic compression process, so which is well insulated, so that S3 remains S4, right? And again 4 to 1 the heat is rejected to the atmosphere. So with respect to the refrigeration system I am telling heat is rejected to the atmosphere, right? Here the heat is absorbed from the sink, right? So from the sink always QL, and from the to the source always is nothing but from the source or to the source is nothing but always QH. And here also from the source from the sink and to the sink is nothing but always QL, right? So in that way actually we supposed to assume with respect to the these conditions, right? Yes. So this is what the reversed Carnot cycle. Again this is nothing but TH1 equal to TH4, right? That is what the with respect to the high temperature, is that right? So atmospheric temperature, assume that sink room temperature is nothing but we are having 15 degrees Celsius. Over here it is nothing but 30 degrees Celsius during the summer season. I supposed to maintain over here. So I supposed to reject the heat energy from the sink. So where actually they are getting the heat energy from multiple sources actually we are having, from radiations and from our body also it is the room temperature get increases, right? That we need to eject it. Yes. So that is what the applications we are having. So this actually I have considered in reversible way, right? How I considered temperature remains constant and Q equal to 0, right? So those conditions is nothing but actually we call it as the ideal conditions or reversible conditions, right? Yes. So the reversed Carnot cycle, how to frame it actually? So the reversed Carnot cycle we are having with respect to the refrigeration or heat pump I said, okay na? So with respect to refrigeration or heat pump is nothing but actually we are having, see what is the COP of R actually with respect to refrigeration, what I said, the desired effect is nothing but QL by, right? What is that? The supplied is nothing but work input, right? What is QL actually? We are having QL divided by what is W in? W in is always nothing but QH minus QL, right? So for simplification purpose, they have brought this QL to this denominator actually. So 1 by QH by QL by QL. So we are having QH by QL minus 1, right? Over here, what is this actually? Over here, we are having COP of heat pump is nothing but actually we are having as QH. Why? Because for the during winter season, the room temperature is supposed to increase with respect to the atmosphere, right? So QH by WIN. What is what is W again? That is what again QH minus QL. So if I bring this to the denominator, what happened? 1 by 1 minus QL by QH. Now it is proportional to TH by QL, QH by QL. QL by QH is nothing but, see, this is TH by TL for the reversible processes, right? This is equal to TL by TH. That's it. So this is what actually we call it as the reversed Carnot cycle. And with respect to the performance parameter, here the performance for refrigeration is nothing but COP. I can able to derive in this way, right? So in this way I supposed to derive it, or simply can able to write this as, see, instead of this one I can able to write TH by TH minus TL. So like that also I can able to write, simple, right? Here also I can able to have TL by TH minus TL for the refrigerator, and this is for the heat pump, right? So these are the highest coefficients of performance that a refrigerator or a heat pump operating between the temperature limits of TL and TH, right? Not TH and TL, TL and TH they have given. That is what the vice versa manner they have given, which we are having, right? So this is what the application of the reversed Carnot cycle with respect to the performance parameter. So whatever the COP of actual, what are the values he got, that I supposed to compare, like in this way. See, the COP of refrigerator and heat pump, right? Whatever it may be. If it is less than the COP of refrigerator and heat pump for the reversible case. What is reversible? This is for the Carnot. This is actually, assume this is actual case, right? That is actual cases. What happen actually? It is irreversible in manner. Irreversible is nothing but actual cases. So we can able to possible to construct it. So if it is equal to this case, it is reversible in nature. What is that actually? COP of actual equal to COP of Carnot, right? So then it is nothing but the reversible way. This is actually not at all possible, right? Okay, na? For comparison, we can able to have, that's it. And COP of refrigeration or heat pump with respect to actual cases greater than the ideal cases or Carnot, reversed Carnot. What happened? It is impossible to construct, right? It is also impossible. This is for comparison, and this is impossible, not at all for the construction, right? So in this way, actually, I can able to compare this reversed Carnot cycle also. So this is about actually the applications of Carnot cycle and reversed Carnot cycle. Simple, the Carnot cycle is nothing but ideal heat engine. Reversed Carnot cycle is nothing but ideal refrigeration cycle, right? Yes. So this is about actually Carnot and reversed Carnot cycle. So this is a very most important parameter actually we supposed to consider for the feasible cases, for the comparative analysis, right? So thank you everyone. So we'll see in the next lecture. Thank you.